of this quiz question. So that quiz question last week, number 3, how does it read? When you read the question, is that any of the barrier? Read the question, look at it, and see, what am I trying to do here? What are you trying to get to? Okay. Need the copy of? So, what does it ask? How are you going to try to answer a question like this on an exam?
Adjusting volume. In the question, adjust volume.
So, Mark, what do you want to use to try to answer this question? Do you have like an equation or an approach or anything?
P1, P1, P2.
Ah. But P and V are staying the same, right?
Why?
Are you looking at number 3?
Yeah.
I'm sorry, I said number 3 because I only graded 3. The last one.
The last.
There you go. That's my bad. I said number 3 because I didn't grade the first one, so I graded it out of 3. I mean the last one, which I guess is labeled as number 4.
That one I use V equals nRT over.
Yeah, I agree with that. And y'all just be aware, my preferences, I'm gonna probably use that more than all the other ones. V equals nRT. Okay, cool. What are we going to try to find? What's the question? Number 4, I should be more clear. What is number 4 trying to find? All right, so let's solve it for volume. How do we do that? All right, so V is going to equal whatever what's this N? What's that stand for? No. Let's go to my total number of moles, R, so it's the same, the T, and then my E. All right, cool. So let's start with the N's. How am I going to get moles here? Okay, now I don't divide, but yes, I'm sure you're doing it correctly. I did a multiply so that I don't have to try to remember when to divide and when to multiply. I always multiply and just cancel my units, right? So I want moles over grams. Let's see, CO2, what'd you use?
44.00.
Okay. Get here. Yeah? Okay. Same process with the next. So for 80 grams. So I got 0.1. Wait.
Units to.
OSA?
Yes.
Yeah, what OSA? Yeah. Okay. Yeah. All right. Now, which of those do I want to plug into my formula over here that we saw? Huh?
Both.
Ah, good, good, good. Now, a couple of different options here. You could find the pressure of CO2 by plugging in 0.075 here and plugging in your other pieces. Find the PCO2, then do it again and plug in the moles of N2 and find the PN2. And then add those two pressures together. Dalton's law says that the total pressure is the sum of all the individual gas pressures. That will in fact work. However, here, it might be easier because the idea behind an ideal gas, so we don't care what the gas is. So we've got 0.075 moles of CO2, and we've got 0.1 moles of nitrogen, but really, for ideal gas law, we just got 0.175 moles of random gas that we don't care what it is. Does that make sense? And so then you can take 0.175 here. What do you use for R?
I use 0.08206.
All right, so let's try it. V equals 0.175 moles. And look, y'all, I know it's tedious to to put it together and cancel your units, but if you don't, eventually it will hurt you, right? But not following the units. So let's see, Mark says 0.08205. What are my units on that?
That is moles.
Moles,
Oh.
liters, ATMs. Yeah. Okay, and then what do I want to use for T? Just this?
Oh,
Oh, what do you want me to use?
geez.
So what would you like me to put here?
270.
Okay, beautiful. Over, what am I using for pressure? All right, so let's look at unit canceling. Let's see. K is in a denominator. Okay, those K's are going to cancel. Cool. Moles, yeah. All right, this atmosphere on top, this atmosphere, yeah, leaving a unit of liters. Oh, okay. Multiply it all out, and you get so F. Your options there, right?
Yes.
All right, beautiful. Make sense, y'all? If you did the partial pressure route, you should have got the same answer. Please tell me if you did not. I believe from last time that I am not ready to go to lecture 4 yet, but I need to go back to lecture 3. Is that correct?
IMF.
IMF, sorry. Beautiful. All right. IMF here. Oh. Really forward design. This one, where we're at? Yeah. All right, so what are these guys? Why do I have color coding up here, red and blue, intermolecular, intramolecular? What am I trying to get at? Remind me from last time. No, don't have it? Somebody help right now here.
Intra is the, was the help molecule.
Yeah, intra is inside a molecule. Within it is
how it reacts.
Inter is between it and other molecules. Okay? Good. All right, so intramolecular, so like holding the hydrogens onto the oxygen for water. Intermolecular is in our thought experiment that we started last time with, where we're holding the water molecules together in the ice cube, or in a drop of water, or even in the gas. Okay? They are non-covalent. What's that about? Good. It's not a shared electron bond. Those are extremely strong bonds, and it's not love. I think we did this, where we talked about increasing the kinetic energy, right? And really, really big now that you can think back to the lab that we did, right? As you are decreasing that energy more and more, you're approaching it as stop, right? And that's our definition of absolute zero. And that's why in the lab, we were trying to project back to where does the motion stop, right? Where does the music die and the dance stop, right? Okay. Okay, I think now we're in new territory. Maybe from last week? Again?
Stop.
Okay. All right. So, not an exhaustive list, and I'll tell you, Murph, when you get to grad school, you're going to talk about other IMFs, and the idea of what's intermolecular versus intramolecular breaks down a little bit, it's not so clear. Okay, so just be aware that it's deeper than this. Just like I get accused of this all the time, especially at Gen Chem 2. Like, well, how about, how do you do this? Is this how you do this? Well, yes, but no. So there's always another level. There's always a more complex answer that breaks what we're trying to tell you. Just like the stuff that we told you in high school, we said, look, it's either a solid or it's a liquid, clear cut. Well, it ain't so clear cut, right? Or a liquid and a gas at a critical point, right? So same things here. I have heard research professors yell and argue at each other about whether a certain thing qualifies as hydrogen bonding or dipole-dipole bonding or some other forms of, there's some others like pi stacking, it's a little different. But pi stacking versus dispersion courses sometimes is a little hard to disentangle. For the freshman level chemistry, we'll keep it to these three categories, okay? These three categories. And I want you to have in mind the whole time that dispersion forces are going to be the weak, very, very weak. Dipole-dipole are going to be significantly stronger than dispersion. And hydrogen bonding is going to be extremely strong as far as these three go, but it's still weaker than an ionic bond or especially a covalent bond, okay? So we're only talking about, I'm talking about hydrogen bonding being extremely strong. I'm saying compared to the other two here, okay? And oh yeah, okay. And I was telling you on this guy to go back and review those structures, right? I think Allison, I have to check, but I bet I have a polarity question on the quiz next week, at least one. So expect that to hit you because you've got to understand molecular polarity. And if we need to do some review on that, let me know. We can. Okay. We did. Oh, that's where we did last week. We started doing some review on that. Okay, good. So hopefully you digested that. Hopefully you went back and read your textbook a little bit to make sure that you're good on molecular polarity and geometry. All that stuff is now going to matter. Okay, so I think I did a dichloro double bond oxygen. I did a methane. What was the other one I did? Oh, right, because I wanted tetrahedral, trigonoplanar, and linear. Right, yeah. Okay, yeah. All right, so let's do those lights that I hate up here again. And let's talk about three molecules that I want to compare and talk about their polarity. Yeah, now I'm remembering exactly where we needed to pick up. So let's do, this is what we did last week, or Monday, right? Let's do over here, my third one. Okay? And then let's do in the middle, let's do dichloromethane. So we've got methane, dichloromethane, and tetrachloromethane. Okay? These things act entirely different. Okay? What do you know about methane? What can you predict about it? Any drag race fans? Drag race fans? Methane fuel drag race. Anybody talk about in terms of fuels, new fuels, environmentally friendly? Nope. So methane is a very simple gas. Burns really well. It's used in a lot of general chemistry, freshman level chemistry problems because it's really easy to deal with stoichiometry. Okay, so be familiar with CH4 method. Okay. What do y'all want me to do structure wise? Still Lewis? What's this going to look like? I'm not gonna go through the whole process again. I think y'all can, now we did it last week, you can go back and review that, but tell me what this is gonna end up being. Draw this a little bigger. So I'm gonna have to make that, I'm gonna draw it bigger because I'm gonna draw some things on it. And over here, can you predict what's going to happen here with this guy, the third one, carbon tetrachloride, CCl4? Can you predict it? What is it going to look? What's the Lewis structure going to look like for it? Yes, say it. No. It's pretty much the same, except
They're more,
yeah, chlorines. Okay, and I guess if you're drawing out this Lewis structure from scratch, you know, you probably end up with your lone pairs on the outside of the chlorines there. But honestly, orgo, we don't usually bother unless a lot of times lone pairs get left off unless you want to like highlight them to show that they're going to be part of a reaction. All right, and in this middle one, let's do this. Let's put it as, let's see, we got 2 chlorines and we've got 2 hydrogens. Right? Make sense? So far? Still looking for my analogies. Nobody's leaning into my analogies for this class. Nobody's interested in dragsters. Nobody's interested. What else did I ask about? Alternative fuel stuff. Yeah. Anybody do off-roading? Anybody ever play in the mud? Off-roading trucks, Jeeps? What the hell do y'all do? What?
I was thinking about,
I can't think
mud
of it.
infusion compared to what I like to do is if you had like 4 men pulling from a center, like these ropes attached to the tires.
Is that what they do?
have different strengths. Not what they do.
Oh, okay. I'm gonna use the Jeep version. They'll probably follow that. All right. Okay. So, all right. So, what are we going to look for polarity eigenvalues? What's our first step to decide if a molecule is polar? Good. And so let's say the electronegativity from the first one over here, from methane, CH4, the electronegativity of carbon is like 2.2, and for hydrogen it's 2.0. I may have this backwards, but they're that close. Okay, they're super duper close, right? So what would you claim about the C to H sigma bond? What would you claim about it? That it is true, but all of these are covalent. Now on what flavor of covalent is it? What type? It is a non-polar or pure covalent bond. Okay? So in the case of methane, we can stop looking, right? We know, we can guarantee that this is going to be a non-polar molecule because, why, Murph? It is the same answer you just gave.
Yeah.
So why?
Sorry, I was yawning.
Okay. So why can we guarantee, we can stop looking here, why? All of the bonds, every bond that we're dealing with there is non-polar. So there's nothing going to make this a polar molecule. Cool? Okay, now, Braden, which, you said electronegativity a while ago, which element up there is the most electronegative on the table? Fluorine. Let's just go pick some an academic period. Because I wasn't sure too. I was just going. Up here is true, yes. So on the table though, fluorine is your most electronegative. And remember, that way more, that way less. So fluorine is the most, well, chlorine and oxygen are pretty close. Okay? So what are you going to probably claim about the carbon chlorine bond? It is covalent, but we use a term, it's not fully ionic. It's in between, what do we call that? A polar covalent bond, okay? And so we will use a little, I hope you saw in Chem 1, the vector notation. Like that. You did see that? Anybody like, I've never seen anybody draw an arrow like that. Anybody? Yeah? You're not?
No.
Okay. All right. So, what am I going to claim about carbon tetrachloride? Is this a polar molecule? It was easy for us to answer the methane because it had non-polar bonds. Is it easy to answer this one? You said what? Why? Say again? They are polar. These are polar bonds, every one of them. So do you think it's a polar molecule? Talk about it, Ellen. You're right.
Since they're all pointing opposite direction, the same force pulling on the carbon, it just bounces.
All right, so this is my Jeep example, y'all. So let's say Murph is pursuing his desire to learn to drive in extreme conditions, right? And let's say he has purchased a Jeep. Okay? Now, Murph gets in an off-road scenario, okay, wherein he has buried his Jeep in the mud. That make sense? So Murph calls me. Like, Eric, got to the thing. Okay, where you at? Right? So let's say he calls me and 3 other friends that have the exact same truck. Okay? And it's important that we have the exact same truck. Because the truck is going to be the chlorine tank. Does that make sense where I'm going with this analogy? Okay, so we come to rescue Murph, right? And I don't know, there's a confusion spell cast on us or something like that. And we hook up in a scenario where we're pulling, one person's pulling that way, another pulls, and another. And remember, these are exact same truck, right? With the exact same track. So what's going to happen? Nothing. Why? They are in equilibrium. This is a really good way to put it. The net force is going to be zero. Okay? Because it's all balanced. So far, so good? So this is, in fact, a non-polar molecule, even though the individual carbon to chlorine bonds are very polar. It's just that this happens to be one of those special cases where they just perfectly balance it. So far, so good. Obviously, I've saved the middle one to last for some reason, right? Don't, go ahead and get in your mind, Admiral Akbar from Star Wars. It's a trap. Okay, I'm telling you ahead of time. Middle one's going to be a trap. Okay. All right. What do you think about this? Tell me any pieces. Natalie, tell me some pieces. What do you want to think about first?
Would it not be because the
Would it not be what?
so we don't even think about the lone pairs?
You can.
Because in this one, we said that they're all pulling the same, they can switch them around.
Okay, cool.
Both sides of the molecule is the same.
Okay, so do you want me to zoom in on one of the bonds first? Pick one. So carbon chloride. So you're kind of talking about this bond here, yeah? And what do you want me to tell? What do you want to tell me about this bond?
Isn't that the polar bond?
It is extremely polar. Okay, let me label it. So we have a very polar bond. Okay, I absolutely agree. This is correct. Okay, tell me about the carbon hydrogen bond. It is not polar. So I'm not going to draw a vector for it. How about the other carbon chlorine bond? Polar. Yeah. Yeah. So remember, so Natalie is falling into my trap. Natalie, don't do it trap, right? You're falling into my trap. Yeah. So I'm not going to draw one for the other. Mercy, what do you think? You think it's going to be? You're like, I know it's a trap, I'm not saying anything. You know? Miriam, do you remember? Why is this? All right, y'all, I'm going to claim that dichloromethane is, in fact, a polar molecule. Why? Yes, very good, Brayden. Yeah, did it. This website that I'm using, National Library of Medicine, so it's a really good site. It's called PubChem, is the easy way to look at it. If you Google PubChem and then your chemical, a lot of times you can find them in here, and they'll give you a two-dimensional structure, but they'll also give you a three-dimensional structure that you can put it around. Okay, now, here's the trick. Here's Admiral Ackbar's trap. We draw this in two dimensions. It's not. This is a three-dimensional molecule. What's the shape? Nope. Miriam, what's the shape? Tetrahedral. Very good. Okay, this guy's tetrahedral, right? You look at, anybody ever play role-playing games, right? This thing looks like four-sided, right? So you've got one atom attached at each corner of the four-sided die, right? Little tetrahedron. Make sense? Okay? And even though, sure, okay, even though it might look like in two dimensions, you have to think about this in three dimensions. And it is going to be off-centered. It's not going to be balanced in three dimensions. Okay, so this is, in fact, a very polar. Okay, please don't be confused by that. Go back and review if needed. Get rid of this. Get rid of this harsh light up here. Okay. All right, cool. And I don't see an order 2. You're all done. Okay, beautiful. She's all done with Orgo. That means all the geometry questions she loves. I may not be exactly what it means, but she can definitely handle them. Okay. Yeah. All right. I put up here, these are called electrostatic maps. You can find these a lot of times if you just Google electrostatic maps. And generally, be careful, sometimes they'll reverse the colors on you. But generally, we'll use blue shading to indicate a positive-ish end of a molecule, and red shading to indicate a negative-ish. So, okay. So this guy is nice and balanced all the way around. This guy is not. Right? So it has a positive and a negative end. And that's the key. So far, so good, y'all? Okay. Dispersion forces, everything's got them. And that's a little bit misleading sometimes because we'll talk about, oh, well, that molecule has dipole-dipole interactions. And it's easy to sometimes accidentally assume, well, okay, if it's got dipole-dipole, that must mean it does not have dispersion forces, and that would be incorrect. The dispersion forces are always there. They're just tiny compared to if it's got anything else. Okay? And this is just, what this is right, it is a four-dimensional space-time continuum differential equation, really. I know you love differential equations now, right? But you can think of it, this is wrong. It's a vast oversimplification. It does not work in PChem, but in general chemistry, you can assume that the electrons are sort of sloshing around on a molecule. And sometimes they slosh more this way, kind of leaving a little positive-y area. And sometimes they slosh back the other way, leaving a different, like a negative area over here. That's not real. It's really a probability function distribution, but you don't need that at the freshman chemistry level. Okay? You can think of it as electrons sloshing around. And they create this idea of an instantaneous polarity in the molecule. The molecule doesn't really have a positive end and a negative end, but as the electrons slosh one way or the other, it kind of leaves a positive end and a negative end over here where the electrons are. Another way to think about this is called an induced dipole effect. And so if you put a molecule near a polar source, it may push the electrons to one end or the other. And that'll cause a temporary, we call it temporary, even though that's a misnomer also. It's not a time function, really. But it's not. It's actually a probability distribution function. So, but nobody does it. Everybody thinks of it this way. Everybody thinks of it as sloshing around, except for maybe the peak and peak. Okay. But you can induce a dipole even if there's not a real. Okay. Then you can get the molecules to stick together a little, not real well, but a little. Does that make sense? A bit? Maybe. All right, look, we'll come back to this one if we need to. This is my temporary dipole. It's not a real, okay? This word temporary is doing a lot on this slide, okay? Because it's going to look like the next one. Oh, I need to point out. All right, and this is the middle. This dipole-dipole interactions are a lot stronger than dispersion forces, okay? So, I told you that this dichloromethane is in fact polar, okay? So let's think about this. It's got a red positive, yeah, colors are switched here. Sometimes that happens, sorry. You've got a positive end and you've got a negative, okay? So let's say the molecule on the left, look, its negative end here can see the positive end on the other molecule. What happens with positives and negatives? What happens with north and south poles on magnets? They attract each other. Well, the positives and the negatives attract each other. So there's a bond set up between those two, right? It's a dipole-dipole intermolecular bond. They don't snap together and become a covalent bond at all. But they can see each other and they can feel that attraction, that negative to positive attraction, and that helps you hold those molecules close to each other. There's a force, just like that ice that we were talking about being held up against the force of gravity. There's a force holding these molecules closer together. Okay? You can orient it the other way so that they can see each other that way too. That works. Does that make sense how they're feeling a positive negative attraction? Maybe? They are quiet. I don't know. I might get my other shot. What do you think? Sounds a lot. It is electrostatic. Yes, you are absolutely right. Okay, Brady said it sounds a lot like, well, you said magnetism, but remember that electrical positive and negative and magnetism are just orthogonal to each other. They're really the same thing. Okay? So yes, it sounds a lot like that because it is in fact that. Does that help? Why do electrons, think back to the beginning of Gen Chem 1, right? You've got a positively charged nucleus, and you've got negatively charged electrons that stay near the nucleus. Why? Why don't the electrons just fly off? They've got a huge amount of energy for their mass. Why don't they just fly away? The charges attract. The charges attract. Same answer. Making sense? So, some other thoughts? Come on, talk to me. Y'all gotta give me your questions. I need your questions. You have your back time going? Am I asking you? Y'all can ask your Allison too, if you want her to ask for you, she's ready. Yes, Mary.
Are there two bonds?
Well, okay, this does go to that question that I had, you remember I told you, like, in middle school, I did not know what bonds were. As an undergraduate, I figured out what bonds were, and then as a graduate student now, I no longer know what bonds are. So it does go to that question. So I would, in fact, call these intermolecular bonding forces. So yes, in the sense that they're intermolecular bonding. No, they're definitely not covalent bonds, and not really even, they're not of the same strength as an ionic bond. They're less than that. Does that make any sense? So depending on how you're using bonds, do they snap these together for them to become the same molecule? No, they do not. Do they act to hold the whole substance together? Yes. Does that make any sense? So if I go up into the stockroom and I get dichloromethane, if I want to go to the stockroom and get methane, I'm not going to find it because this is a gas. You'd have to have this in a pressure cylinder, right? But this, there's a jar of this sitting in the cabinet in the stockroom. It's a liquid, okay? Because this molecule and this molecule are attracted to each other and kept in the liquid state at a much higher temperature than that. So it is an intermolecular bond in that sense, but they're still separate molecules. Does that help? Other questions? I'm going to go on to hydrogen bonding, but y'all have me come back if I need to. Oh, yeah, okay. Let's sneak up on it here. This is actually what I was talking to Miriam there about how the boiling points, look at these boiling points. So apparently mass is my x-axis here. Apparently how heavy a molecule is does affect its boiling point. Do you see the function here, the correlation that heavier molecules take more temperature to get them to boil? That makes sense, right? That let's see, heptane has a molar mass of 100, right? And so its boiling point is 98. Does that make sense? That's 98 C. So heptane boils at about the same place that water does. Okay? But something much lighter, like ethane, has a molar mass of 30. So its boiling point, is negative 89 C. Okay? It wants to be a gas. Does that make sense? And everything else is arranged in between. You see what I'm doing graphing these guys? Does that make sense? Please digest this because I'm going to make this graph more complicated in just a second. Okay? Yeah? All right. But look what happens here. The blue ones have dipole-dipole interactions. Even if you pull up the laser pointer here. Looking at, let's see, ethanol has a molar mass of 46. Okay? Make sense? And the top part, propane. Anybody got propane cylinders at home? Anybody got gas cylinders? Good. I was beginning to worry that these. I don't know, but okay. So propane cylinder, right? That's gas in there. Well, it's compressed so that it's liquid-ish, right? But if you turn it loose, it becomes a gas, right? Its boiling point is apparently very low. Does that make sense? In fact, boiling point for propane is negative 42 C. Okay? Its molar mass is 44. Well, you would expect ethanol with a molar mass of 46 to have a very similar boiling point, right? Right? But if you go this weekend, right, and you pour your golden grain into a glass, right? You know what golden grain is?
Ethanol. It's the alcohol. Oh.
Oh, I said polymer because it's like everywhere, it's all pure alcohol. But if you pour that into a glass, does it boil?
Should.
It's, no, don't drink that if it's boiling, please. Okay, it burns enough if it's not boiling, right? Okay, but look, its boiling point is 78 C. The molar mass is almost the same, 46 versus 44, it's almost the same, but the boiling points are drastically different, and that's because ethanol, I'm gonna erase it. Does anybody want this before I erase it? Okay, ethanol structure has got a polar. It's propane. Similar structure, except those are all non-polar, so propane doesn't have any polar structures. So propane, this molecule of propane doesn't have the positive and negative ends to attract the next propane over. Ethanol does. Does that make sense? That's why your ethanol is a liquid, not a gas. Okay? Where that else?
You see that one more?
Yes. From where?
Like, wait, just.
Okay. So propane, the structure on the bottom there, is all carbon-hydrogen bonds. And probably when I was asking about our methane that I partially erased up there, Murph told us that, look, carbon-hydrogen bonds are each individual one. Those are non-polar bonds. So we can guarantee that that propane molecule on the bottom there is totally non-polar. There's no positive end, there's no negative. So one propane molecule can't use a positive end to attract the negative end of another propane molecule because there is no such thing. All it's got left is its dispersion forces, which are extremely weak. However, ethanol up here does have a very polar end and has a very negative zone, leaving the rest of the molecule more positive because that end is negative, because the electron's going to pull up there. Okay? And so there is a negative end on an ethanol and a positive end. And the negative end on one ethanol molecule can attract the positive end on the next ethanol molecule, trying to hold them together as a liquid instead of just letting them boil away. It's all about those forces, okay? Yeah? Yes, Mary?
So how come hydrogen is the strongest out of them? If dispersion has like the positive and negative?
Very good. This is an excellent question. All right, so let's try to process the question that Mary was asking. She's leading to the next piece here. Remember, there are three of these, right? The first one is dispersion, which everybody's got, and it's all you're left with in the case of propane here, right? And then I've been talking about how strong the positive-negative interaction is, right? And Miriam's like, well, wait, there's something else coming, right? And she's right, there is something else coming. Why is the hydrogen even stronger? Let's talk about that. So let me sneak up on it, Miriam, and make sure that you tell me whether I end up answering, okay? What I have here is a graph of, let me point out on the periodic table here what I'm doing. So with the red, okay, with the red series there, I'm taking iodine here, you see where it is on the table, and I'm bonding it to hydrogen. So HI, iodic acid, has a boiling point. What is it? It's like, it looks like it's like negative 40 C. Does that make sense? But then as I go up to bromine, look, it gets significantly lighter, right? Iodine's super heavy because it's down low on the table, right? Bromine is not quite as heavy, although it's still pretty heavy, right? So HBr should be easier to boil than HI. Does that make sense? And it is. So HBr has a boiling point that is even lower. It's like negative 60-ish C. Does that make sense? You see my trend here? And then HCl, even lower, negative 80 C. All right, and then I didn't put HF on there. What's your, so looking at my trend on my table, what do you expect here? I, BR, CL, now F, HF, where would you expect it on the table? What would you expect to happen from this trend?
It would be,
Yeah, that makes sense to me, right? Like we would, it's not perfect, but we might expect it to still be like negative 90-ish. I don't know, just guessing. Does that make sense? All right, let's do the other. Let's do green. See, I'm going to do the same thing. H2SB, right? H3SB, H3AS, H3P. It's hard to see, right? And then in H3, what do you expect? Where would you expect it to be? Looking at the green trend, again, same idea, right? Maybe negative 100. Does that make sense? Now let's look at the blue. What is H2TE's boiling point according to that table? About zero. Cool. What is H2SE? I'm going up the table, just like I did on these others. H2SE, what do you see? Negative 40, okay. How about H2S? Negative 60. Okay, how about H2F? Wait. No. You know what the boiling point of H2O is. What is it? Huh? Well, what would I expect from this trend? Yeah, you would expect it to be somewhere between negative 50 and negative 100, maybe like negative 75-ish, right? Does that make sense? And it isn't. It's 100. It's positive 100. What's going on with that? Why do these not end up where they would be projected to be? And the answer goes to what Miriam was asking: hydrogen. This third kind that I claim is so incredibly strong. Look at what happens to my trend. Okay. So we can measure these, we can plot them. Now, Miriam, what we do in science is we'll make a prediction, right? And then we'll actually go test it and see. Well, I might have made this prediction from the trend, right? And then I go measure it, and I'm like, what the hell? Why is it, right? And so now it's time to go back, okay, now we gotta figure out what's going on, right? And so here's our best guess as to what's going on with hydrogen bonding. Hydrogen itself is extremely small. Okay? Also, think back to your atomic electron configurations. Let's look at the electron configuration for atom. Remember? 1s2, remember this? 2s2, 2p, 6, 2p4, right? Yeah? Okay. So 1s2, 2s2, 2p4. Stop. There are no groups. And that's the key. Oxygen is also small. Fluorine. Fluorine has only got principal quantum number 2, second shell in the Bohr speak, right? It's small. Nitrogen, same answer, small. Okay? And extremely electronegative. Okay? So, now we get an idea of what's called charge density. So, if you take a certain amount of charge and you spread it over a certain amount of surface area, you get what's called charge density. Well, since you are spreading, let's do the fluorine. We got fluorine, -1 charge, right? spread over an extremely small sphere, right? That's a really, really high charge density. Whereas chlorine also has -1 charge, but it is a much, much bigger ion than fluorine. So you're spreading that -1 charge over a much larger surface area. Okay? So the charge density on this is not near as high. And then it gets even less out here. Right? These get sloppy. Same thing with oxygen. You got -2, but you're spreading it out over a very small surface area. And so it's a really high charge density. Now, if you take and you interact your hydrogen with it, you've got a very, very strong positive ends, right? Very small and very high charge. A very high charge over a very small surface area on the oxygen end. Also, we think that's what causes this break in the trend here and causes a hydrogen bond to be so incredibly strong.
Would we expect these to appear in polar or non-polar bonds? Or polar?
Well, they're definitely polar. Hydrogen bonds are an extreme version of polar bonds, of dipole bonds. Does that make any sense? Is there a Saturday night racing anywhere around? Like, you could probably find a place where folks are out racing the little Hondas, right? Maybe somebody's got a little, what's a hot one right now? It's a hot car right now. Maybe somebody got old school from my days and brought out like an old GTO or something like that, right? Right? Yeah, what?
Okay.
A Hellcat? That's pretty hot one now, right? Okay, cool. So you got some cars and some hotter cars, right? And then somebody shows up with a Maserati. We're in a whole different class, right? Same idea. Hydrogen bond is a whole different class. It is a dipole. It's just an extreme version. Okay? Make sense? Maybe? Bit more. Or somebody shows up with a top fuel dragster. Okay? The Hellcat doesn't have a chance against a top fuel dragster. Okay. So we think it's about the size of the ion speed. But lucky for you, there's an easy way to remember it. Okay? Only fluorine, oxygen, and nitrogen can have fun, FON. See what we're doing there? Okay, giving you an acronym. We only consider hydrogen bond to be active when you have a hydrogen attached to an F, a fluorine, or an O, an oxygen, or an N, a nitrogen. Okay, anything lesser than that, we're just going to call it dipole. That help? Any? Why do you care about hydrogen bonding? I mean, I care about it as a chemist and a geologist, right? Well, why do you care? Mercy, what's your major? That's what I thought. Why do you care about hydrogen bonding? What's the code for how Mercy was made, put together? What's the code? Well, we do need it for water, you're right. But what's the code for how your parts came into being? Thinking about biology. Biology got a code for how y'all make things. DNA, right? DNA is all about the hydrogen bond. See this all the time in biology textbooks, right? You ever thought about it any deeper? Well, okay, what's going on with these little colored things here? Tell me about these colored things. Biology people, come on, your time to shine, biology people. Tell me about these colored things in the middle. What's going on? What are those? Okay, they are. And what else? Why are they different colors? I don't heard it. Allison, tell me please. Valerie, have they heard of this?
They're just now in biology, one they haven't gone in yet.
You didn't know about this in high school biology?
Well, yeah, that's been, previous.
And you don't like biology, right? That's why you don't mention it, right? In high school biology, what are those color things? Seventh grade life science, what are those color things? Good God, y'all, come on. Yeah. There's the base pairs, right? And then one pair with each other, right? Why? Be a scientist and ask the why question. Why does, if one goes with, why does C only pair with G? Why does the C pair with A? Pair with why? Hydrogen bonding is definitely the key. The dotted lines, hydrogen lines. They're what keep your DNA zipped together. Okay? So some of the research that I did in Birmingham is we would take and we would actually take apart a DNA strand and splice in other pieces of DNA to genetically engineer, or I was actually genetically engineering organisms in grad school. We were researching human proteins. SRSF1 is the name of the protein I was working on, and so we needed a bunch of SRSF1 protein in order to put it in NMR and try to determine its structure. It turns out that when you're getting your research approved, they won't let you grind up humans to extract proteins. They don't really approve that, but they will let you grind up E. coli bacteria. So what we did is we genetically modified E. coli bacteria to produce the human protein SRSF1. And this is the way we did it, by unzipping the DNA, right? And splicing in the human piece in it and then re-zipping it. And so what we were doing is we were breaking the hydrogen bonds, right? But remember, they're very strong for internal. So we could heat it up basically to break these bonds and not break the covalent bonds. And that was the key to making the research work. Does that make sense? Yes.
Wait, how did you unzip them but not?
Say it again.
How did you break them and not break the other ones?
Genetic sequencing device. So we basically just heat it up. We got one upstairs. I can show you in the biochemistry lab. You know Dr. Gallard? One of your biology professors. He uses it all the time. So he's doing this here too, right? But so basically you run it up. I think we were running up to 90, I want to say it was 98C. It might have been 95C, right in that zone somewhere. And what makes that work is an enzyme from a deep sea organism that's an extremophile that can actually work at those temperatures. And so you're able to unzip the DNA at those temperatures, and then you layer in the DNA that you want, and it basically cleaves the other, and you have to play with it a little bit as you go and get it to extend out and break some bonds and not others. And so it's a lot of back and forth, trial and error, trying to get it extended out right. Does that make sense? And then you cool it slowly, let it congeal back together, and it'll reform the helix. Does that make sense? Probably deeper than we need to go with this, but it's cool research though, and I can show you a bunch of stuff that we did. Other questions on this? This is an example of it in water, right? And Miriam mentioned this too, that we also need the hydrogen bonding for water to be liquid on our planet. Right? It shouldn't be from that mass function that we had a while ago. It should all be gas. We shouldn't be living in the water system. But you're right, because of hydrogen bonding, it is a liquid on this planet. So we do have like, as we know it with other. Okay, that is hydrogen bonding. And we go on a little bit to some properties ideas. Okay, do you want any more on the hydrogen bonding before we? So properties are how we interact with things. There are these three things that we juggle a lot in chemistry. We've got properties of things, like I can check the viscosity of water. You can check the viscosity of dichloromethane versus the viscosity of tetrachloromethane. I can look at how those interact in a system. I can put them in a machine and compress them or shear them. Those are properties. And we have the submicroscopic, so that we're actually thinking about what the structure of the individual molecules are and how those are interacting. And then the other piece, the other corner of the triangle is how do we represent that, the symbolic side. And so I'm just trying to tie all those things together. The way we get to all of these ideas is by looking at properties like viscosity. Now, what is viscosity? Yeah, real close. Put a wall in your car? Oh. Put a wall in your car? What do you put in? Got some numbers?
Yeah, it's like 10.
You got 1030. All right. I got a different number that they put in theirs. So we just bought a little Honda, and it takes 0W20. Seriously, right? My truck, I put in 2050, right? So now wait, what am I talking about here? These are viscosity measurements, okay? And so the higher viscosity means it resists flow. So the numeric value is how much it resists flow. So if I put that 20 weight oil in my wife's Honda, I'm gonna get in trouble because it's gonna resist flow too much and it's probably not gonna flow through that little bitty engine, right? And then things are gonna get worse. Make sense? So think of these properties, you gotta look at them and see what does it say? High viscosity has strong intermolecular forces, so it's hard to break one molecule loose from another molecule and get it to flow away. You see how that starts to inform us about what we're trying to make interpretations from the actual properties that we can measure, right? And then you can see a trend here with how polar the molecule is versus how this is. You ever see one of these guys? What's going on here? What's that?
I just learned on small.
Did you? Good.
They have like hairs like on their legs.
Yeah.
This is stuff from-
Ha.
It's like.
Well, what do you know about water? What does it have that most things don't have? I mean, hold on. What does water have? Most things don't have. Extremely high clarity. In fact, it's got a special case that what? It has what are these? Hydrogen and oxygen. Hydrogen directly bonded to oxygen, so that probably qualifies as what? A hydrogen bonder. Yeah, it's got hydrogen bond. What do we know about that? Very strong. So the forces here between individual water molecules are really strong as intermolecular forces go, right? And so if that water strider can spread out over more water molecules, it's enough to keep it above water. And it's all about those intermolecular forces. Hydrogen in this case. Now you can get back and you can like take it to the next level. Where did you hear about it?
Biology,
Which biology?
pathology.
Okay, now you can go back and add to. Be brave, you gotta speak out, right? Find your voice. Do you have more voice in biology? You feel more comfortable there? You don't?
I'm not a big sports person. I'm not strong.
Don't sell yourself short. You're not confident yet, I see that. That doesn't necessarily mean you're not strong. Okay. I could shake for that.
No, I said it's easy.
Okay. Another one that you've seen, even if you didn't realize it, is this cohesion and adhesion idea. If you're measuring that burette, remember the burette where we did the titration to the pretty pink pillar in Chem 1, right? How do you read the burette level? Notice the curved bit in there, it's called the meniscus. Okay, so how do you read that? At the, where the derivative equals 0? That's not really what you're saying. Sure. Okay, well, what's going on there? Wait, what's going on? Well, it's because you've got forces going on, and it's a balance between the forces that are holding the liquid against the other material versus the forces that are holding the liquid together. If you were drawing up something like mercury, right, then its forces are such you get this effect instead, because it doesn't like to interact with glass. And so the meniscus is actually upside down, but it's all just a force balance thing. Okay, all right, that's it for that lecture. So, how long do I have? Allison, oops. All right, not long. Well, let's look at it at least, and we'll go from there. I am looking at when do we do exam? We're getting close, y'all. Good. Thinking. Maybe then, I'm not sure. I'm still messing with those. But we've got 6. We got solutions, solubility, condensed phase we just finished. This thing's broken. Phase diagrams. So we've got basically 3 more lecture sets and then example one. Okay? So we may be looking at maybe as early as a week from Monday-ish. Okay? So start thinking on it.
Do you do an example session at all?
I was hoping you would be.
I mean, I will be, but
Okay.
those I can't make it.
Try to make it.
It always does.
So Alice was talking about because last semester in Chem 1, we were able to do a lot of exam review sessions in class, but in Chem 2, we ran out of time. So I don't know if we can have, well, you and I can sit down and talk about our schedule and see if there's time to put it in your but I really want to save more time for the equilibrium, stable stuff with this group, it looks like to me.
So I asked,
So yeah, my first option would be please go to her review session, Michelle.
Yeah, we'll have a good time.
All right.
We'll plug in.
Okay, so make sure you do read the sections on phase diagrams. Now, I've introduced phase diagrams a little bit, right? So you know what they are. The ones I introduced last time are basically temperature versus pressure. That's not the only way you can do these. You can do them temperature versus composition. We did a lot in geology. You can do any kind of system that you want. Phase diagram just means that you're delineating zones on that diagram, which are one phase versus a different phase. That's what makes it a phase diagram. Okay? We'll go there next case study. If y'all not watching next case study, that's really cool. Okay, do take a look at this. Like I said, we'll take the time that we have and get in because I think we're already behind, and we'll pick up from there next time. So this is a simple one that only has the three phases that are also simple states of matter that you're used to: a gas, a liquid, and a solid. Right? And so these arrows that I have drawn across it are transitions, or we call them phase changes. Okay? So you have a phase change. So let's assume this is water. I'm not asking what's really in this. Okay, but let's assume it's water, and we want to change it from what phase is it in right now? Liquid, just liquid water, aqueous phase. And we want to change it into a vapor phase, a gas. We would do, what's my verb? Well, we would do what to it? What's that called? We would boil it, right? You could also call it vaporization, okay? So start to get familiar with the terms your textbook uses: vaporization, boiling, same thing, okay? What's this? Melting is a phase transition from what to what? Oh, it's a liquid. Okay, cool. Freezing is from liquid to solid, right? Okay. Now look, for some reason, I don't know that it will bother y'all, but for some reason in the past, I've had people get confused, right? If I say, Natalie, what's the boiling point for H2O in a normal atmosphere system? In degrees C. What you said? 100 C, yes. Okay, 100 C. All right, but then I'll ask, what's the condensation temperature for H2O in 1 atmosphere system? Everybody's like, I have no idea. Am I supposed to know that? Well, what's condensation? It's just the other direction. So what's the condensation temperature for H2O? 100 C. It's the same answer. Does that make sense? So please don't be confused by that. If I say, what's the melting temperature for H2O? It's 0 C. What's the freezing temperature for H2O? It's also 0 C. Does that make sense? Now, that's at 1 atmosphere. We're going to change that. This one may not be as familiar to you. Sublimation is going from solid to gas. Now, I'm going to stop making assumptions that y'all have party experience like I do. But a lot of times at parties, people will put dry ice out to make the fog effect, right? What's going on? Is the dry ice melting into a liquid puddle on the stage? Oh, why not? It's solid, right? Isn't it solid to start with? Well, why is it melting into a liquid? It's sublimating it. It just goes straight from a solid to a gas, okay? So, the sublimation, deposition, okay, those are opposites. Does that make some sense? Let's see. And you know me, I'm going to use subscripts for things. T sub M for melting temperature, or some other cryptic usage that you could ask me about. Oh, this is a good point to put in. Okay, remember on an exam, right? Natalie, you see T sub M. You're like, what does he mean by it this time? It never hurts you to ask. Okay. Now, please be aware, I may not tell you what you want, right? But it's not gonna hurt you to ask. Anything you see that I've been cryptic about, please do ask. I don't necessarily mean to be cryptic about it, okay?
Also, ask, sometimes tests are just long.
Yeah. Be brave. Tell me when I screwed it up, because that happens, okay?
Sometimes you forget to put the right answer even in the.
Yeah, which one was that?
That was.
Was it 3? And I was like, oh, y'all, okay, this doesn't have a right answer, so just write in your answer. And somebody circled B. So, nothing I can do about this. Okay. They did. Yeah. All right. So I'll stop beating it up for a little while now. I want you to read this. Remember that it's statistics. This goes back to that Boltzmann idea. And this was that thought experiment that I was saying that if somebody over there, we had their water cup and we left it at room temperature for a month and it all evaporated. But I'm not going to claim it never reached 100 C. I want you to dig back into your text, look at Boltzmann distribution, try to remind yourself what's going on with that. Read the phase diagram section. Another thing, watch for a thing to come out this week about lab next week. Next Monday, is that right? Okay. So we need to run a stoichiometry problem before lab. Okay? So you get to make an airbag. How do airbags work? You run your Hellcat into a pole, right? What happens? We hope the airbag goes off. What does that mean, the airbag goes off? What does it mean? How? There is, in fact, a chemical reaction, sodium azide, chemical reaction. We're not going to use sodium azide because it's kind of dangerous. We're going to use 6 molar HCl, which also got it. Okay, we're going to use 6 molar hydrochloric acid and baking soda. Remember the high school, middle school experiment, and the volcano, right? Well, it's that reaction, right? The HCl plus HCO3 to make carbon dioxide gas. You're going to predict how much gas you need. Okay? You. Look at that lab. Nobody wants these. Well, some of them are in the night class. I better keep these for now. All right. Huh? I don't either. You need to grab it for that reason, Brandon. I was like, what the? I didn't really dig into it. I just put your hands on my eye. I need to look at it and tell me what it is. It is there somewhere. You need to look at it.
I realized just how bad it is.
Okay. What'd you get?
I don't want to say.
Oh, why not? Be brave.
It's actually impossible to get my hands right.
Is it? Oh, what'd you get? Down one enough. How's it Braden's?
I somehow lost liters in my calculation.